for a couple of years or so now, and even a little bit more. And in the process, I'll mention a few results, but really the purpose of the talk is to give a kind of a panorama of these things that have caught my attention. I think there are really just sort of a lot of questions one could ask. I'll ask some, and maybe others will occur to you. And everything has to do with this contrast between reversible and irreversible dynamics. And the subtitle here gives you 3 of the example areas in which we will touch. So the theme is going to be this. Oh, and by the way, I am going to speak very fast because I don't like it when speakers go over, and I have sort of a lot to fit in. That should not be regarded as any kind of discouragement from you breaking in and just asking, as we mentioned. So we're going to want to distinguish between sort of 2 extremes on dynamics. We're talking here about stochastic dynamics that tend to settle down to a steady state of some sort. And I'm going to contrast between really 2 sort of extremes of what one can have. And one, I'm going to suggestively use the phrase passive, that these are passive dynamics. Also, the word equilibration is often used for these processes. Is that, and for those who know something about this, is what we're going to call reversible or detailed balance dynamics, and that converge to an equilibrium. At the larger, more expansive sort of regime, we're going to allow for active stabilization. These are in general irreversible dynamics, so they do not satisfy a detailed balance. And I'll say more what that means. I'm not actually assuming that you know what that means, but that also converge to a steady state. Okay, so we have this very kind of simple nested sort of Venn diagram where in the inside there's reversible dynamics. They're green because they're sort of very nice and gentle and easy to deal with. And then there's red, which is sort of general Markovian dynamics. Okay, and then there's going to be some intermediate category that I'll describe later. And so there are a few questions you can immediately ask, which is how expressive are these different categories of dynamics? What types of systems can fall into them? And if you have dynamics in one of these categories, how rapid is stabilization, namely approach to the steady state? Or if you take one of these systems and then you shake it up all the time with some maybe noise kind of impinging, how much noise can these systems withstand and still resemble their non-noisy selves? Okay, so these are a series of questions. The outline of the talk is going to be something like this. I am going to first spell out for you really what passive stabilization is and what reversible dynamics are. Then I'm going to talk about the tools that we have for analyzing those. I'm going to contrast that then with active stabilization, and I'm going to give you a few examples of those. Then I'm going to switch over to the mathematics in terms of what tools we have for analyzing these kinds of dynamics. We'll talk about Frobenius and some other things. And then I will come back, and the third part of the talk, I'll give you 2 case studies in non-equilibrium, in what's called NES. I'll give you the acronym later. Okay, so within these irreversible cases. Okay, so that's the outline of the talk. A little bit of introduction, then some math, and then back to other case studies and what we can learn about these case studies. All right, so what's the simplest kind of a system we can talk about in passive stabilization, or maybe at least what's the most familiar type of system to those of us in sort of computer science and allied fields, would be something like the Ising model. So you have a system, it has a Hamiltonian energy function. It's a sum of local terms. So the energy of this kind of picture is like, there are spins, they're up or down at every location. The energy of a configuration is the sum over neighbors of some energy cost that's associated with the bond between them. And on the left, you see a picture, which is not mine. I took from some paper where they actually did simulations. And that's a picture of a low energy state in the ferromagnetic Ising model. The ferromagnetic Ising model is where every pair of adjacent spins prefer to be pointed in the same direction. They don't care if it's up or down, but they like to be pointed in the same direction. And this would be a typical state that you're seeing at a low temperature. It's highly biased toward one of the 2 colors, highly biased toward red in this case. But because there are many more configurations that have a little blue in them than those that have no blue in them, there's sort of a balance between entropy and energy, and what you tend to see is actually something like in this picture. Okay, So that's what you will see at finite temperature. And at finite temperature, the system is not in a definite state. It's not in the ground state. It's not all spins aligned, but in this probability distribution that favors low energy states, but is not entirely there. And that's what you sort of see. And this energy versus entropy trade-off is expressed, and you can see at the bottom of the slide. I hope you see my mouse over there, in this expression for the distribution, that the probability of a particular state is proportional to e to the minus the energy of that state. Okay, so very low energy states have higher probability, and this tails off exponentially in the energy, with the temperature playing an important scaling role there. Okay, so that's perhaps a reminder, perhaps of things you've seen before. Now, why is this the Gibbs distribution? Where does one pull this out of a hat? This particular kind of distribution, because this thing that we call a Gibbs distribution or Boltzmann distribution is just absolutely universal to this area of study. And I know there are a bunch of people at TFR, Piyush, and not only Piyush, who know a lot about this. Why are these things universal in these sort of StatMech type problems? So there's really two explanations why we come in across these all the time. So there's a physical explanation, that this is actually the unique fixed point under when you're in what's called the canonical ensemble. You're in contact with a heat bath at a particular temperature. Okay, but you can still trade energy with the environment and nothing else. Everything else gets forgotten. Then this is actually a unique fixed point of distribution. So that's one explanation. Now, there's another explanation that has to do with why we tend to deal with these kinds of distributions also in computer science, sort of a more algorithmic explanation, which is that there's a really natural class of algorithms that give you that converge to this as their steady state, or actually equilibrium. There's the Metropolis or Glauber. They're slightly different, but not in any interesting way for our purpose. Where you move when you have two adjacent configurations, and adjacent is in terms of what your algorithm is willing to do, what Bitflip is willing to do, that you make the transition back and forth with a probability that depends upon the ratio of the two steady, the two probabilities in the Gibbs state. You'll notice that it's actually hard to figure out what the Gibbs state is because of a normalizing factor, but the ratio between two configurations, between the probabilities of two configurations, that's what I'm kind of circling with my mouse here, that is very easy to determine. Okay, and that's the beauty of it, and that's why this algorithm has been in use for, I don't know, 3/4 of a century now or so. Okay, so you can decide with what probability to switch from the configuration on the left to the configuration on the right without difficulty. Okay, so this p sigma tau that I've defined in this equation is a row stochastic matrix. It's a Markov chain, and the Gibbs state is the unique steady state of these dynamics. So this is a fine rationale to some extent as a computer scientist, but it's a pretty limited rationale. If you try and reinterpret this rationale in physical terms, it's sort of strange. It is not actually interactions of a system with its environment through a thin boundary layer. It's actually reaching into the system and flipping bits right in the middle of the system. It's a very unphysical. It's convenient, but it's very, very unphysical. So these are really the physical and algorithmic explanations are quite distinct. Now, we can talk a little bit about what this has to do with maybe computer science in terms of how we actually store memory in systems. So going back to the ferromagnetic Ising model, there are actually two lowest energy configurations, and they're really hard to get from one to the other at low temperature, right? So the mostly red and the mostly blue, you have to go through some very high energy states to get from one to the other. And that's why mostly red and mostly blue are what one calls metastable states. They last for a long time. The Gibbs distribution on a finite size magnet like this rock I have a picture of here, the Gibbs distribution is actually uniformly distributed on both of them. But in physical terms, that has almost no meaning, because you'll sort of really just be in one of them and never make the crossover to the other side if you're at sufficiently low temperature that the system magnetizes of its own accord. All right. So so that was one rationale, Ising model, that maybe you're hopefully many people here are familiar, and that's why I led off with it. But I actually want to tell you a little bit more about another example. I think this example is less familiar to computer scientists, although maybe it is surely more familiar to some of the applied math people that you have. So this is something called the Fokker-Planck process or equation. So this is models the following kind of situation. You have a molecule in a fluid, and it undergoes these random collisions. Okay. Now, the fluid just kind of sitting there, and your particle is moving around. And if it has some velocity, it tends to get more often reflected sort of against that velocity than with it. Right. It's more likely if you're running really fast through a crowd, your next collision is likely to be, on your nose and not from behind, because you're going fast. All right. So the fluid around you, or the crowd around you tends to confine your velocity, because the collisions kind of will go against it. And the way we model it in this process is well, I give you the equation here, so it's actually convenient to work. So this is the stochastic I'm starting here with the really stochastic equation here, which is that the differential of the velocity is the sum of two components. The first component is this deterministic damping, which is sort of minus the gradient of this potential function phi. So that's what tends to act against your, you're running fast. That's what tends to act against you is this essentially potential function on the velocity, which we're going to take to be quadratic throughout. And then, but there's another term, and the other term is the heat or the noise term. And that's just what's called a Wiener process. That's just something that's kind of bouncing you around. So you never really settle down to not moving around at all, because you're at finite non-zero temperature. So there's always this kind of Brownian motion that kind of pushes you along. Okay, and this is the sort of the stochastic equation that dominates this process. Fokker-Planck is the equation that we get when, instead of looking at this sort of stochastic equation, we look at the density of the velocity. So probability density of the velocity, and we get this kind of equation, which I don't want to break out for you, but it has a steady state, and that steady state is in fact a Gaussian distribution on the velocity. If the confining potential had not been quadratic, then it won't be a Gaussian. It'll be e to the minus that. But this is the general term. Okay, so analysts have spent a lot of time studying this and related equation, and verifying that this is the steady state is an easy thing. You can do this, right after the talk if you are so eager. But the controlling convergence rate to the Gaussian distribution is another matter. That's actually pretty sophisticated, but it's proved using tools that are familiar to us in computer science. In fact, we got them in large measure from the analysts, as the log sub-11 inequalities. And all of this is sort of in the spirit of the Boltzmann-H theorem, which is about a slightly more sophisticated setup. And it just says if you let a fluid sort of thermalize, then this is what will be the steady state of velocities of its particles. Okay, and this is going to be a reversible process. The third example I want to give in this kind of very rapid tour of passive stabilizations, what I'm calling them a reversible, is an example that's near and dear to the heart of many theorists and combinatorists and probabilists, which is sampling graph coloring. So I give you a finite graph, and let's suppose it has maximum degree d, and you are supposed to give me a random valid coloring of the graph. That means no two neighbors share a color. And you'd like to sample uniformly from these. And for those who haven't taken just the right course, that's equivalent to So approximately sampling from the uniform distribution is equivalent to approximately counting how many colorings there are. Okay, so these are both interesting questions, but they're the same question. And there's a natural Markov chain for doing this coloring. Okay, this is if you spent a few minutes on this question, this might be the algorithm you would come up with when the number of colors is sufficiently large. Okay, and by the way, I should just point out that if you're trying to get away with a small number of colorings, then of course you're up against NP hardness of there even existing a coloring. So that's not where we're working. We're working in the regime where there's sure to be coloring. So where Q is certainly larger than the degree. And in fact, this algorithm will work not even quite at the degree. I'll say in a second when, but the algorithm is really simple. You take the graph, and if you want to, whether you have a valid coloring or not, the burn-in period till you get a valid coloring, but even suppose you currently had a valid coloring, but now we want to converge to uniform. So what you do, you take any vertex, randomly, and then you randomly recolor him with a color that none of his neighbors use. Okay, so he has D neighbors. That means if Q is at least greater than 2D, then you have more than D choices. You sample uniformly from those and continue. And this is known actually to converge not only at 2D, which was a wonderful result, but even all the way down to 11/6 D minus some tiny term. Okay, it's a very frustrating result because or question, because this question has been around for a long time, and it could be that this algorithm works for D plus 2. Okay, so I just have to mention that. That's not the topic of my talk, but I just have to mention it. Anybody looking at this, has got to waste a little bit of their career trying to solve this problem. And so, all right, let's get back to where we're going. What I want to point about this algorithm is not this open question that's going to ruin your career, but I'm sorry, what you're going to solve, but the that there's really a huge literature on these graph colorings, okay, and the sampling from colorings. And some of those methods are not passive. Some of those methods are quite different, and in fact, don't look like this at all. But in the realm of sort of these kind of Markov chain processes, to the best of my knowledge, they're all these reversible processes. So if you think about the process I just described to you, this recoloring, if you had been in a valid coloring already and you can jump from color C to color C prime, you could just equally with the same conditional probability have gone from color C prime to color C at that vertex, right? The same flow forward and backwards. So this is what I'm calling a passive convergence to equilibrium. Okay. So what I've been dancing around this. What is special about these kinds of dynamics? So I keep calling this an equilibrium, and I just really want to actually write down the definition of detailed balance because this is the topic. So although I know many of you know this, I'm just going to have to say it. So what detailed balance or reversibility means is this: when you are in the stationary state, and I'm assuming uniqueness of the stationary state and so forth. Okay, so then you take any two states, U and V. The pi of U is the steady state probability. Pi of U times the conditional probability of going from U to V is equal to pi of V times the conditional probability of going from V to U. Okay, in some sense, the flow across this edge is the same in both directions. Okay, that's what it means to be reversible. That's what it means to be in detailed balance. And the word reversible is being used here in a very different sense from what it means like in thermodynamics or something. Okay, so it's kind of very unfortunate, but this is what it means. Okay. Now the reversibility condition can be rewritten if you just do a conjugation of or similarity transform on the matrix, taking into account the degrees of the vertices, and you form this new matrix P bar. Then that P bar is symmetric if and only if the process, the Markov chain is reversible. So really thinking about reversible Markov chains is, after this kind of rebalancing, the same as thinking about these kinds of matrices which are in fact symmetric. And this is what shows you that the picture at the bottom. This explains the sort of the picture at the bottom of the slide, which is that on the left-hand side, you see a process that is in detailed balance, or it's reversible, and the arrows are meant to suggest that there's about the same amount of flow going between A and B as between B and A in all these cases. Whereas on the right, you see that there's kind of a cycle. There's kind of a probability flow around the cycle. That's what happens in these irreversible processes. The significance of reversibility goes back a really long way. So it was first talked about by Lord Kelvin in 1854. And then, about 90 years almost went by until Lars Onsager gave a kind of a physically motivated argument why, in fact, when a physical system is in thermal equilibrium with its environment, again, this is kind of what we model by the canonical ensemble I mentioned before, why that kind of system should actually be in detailed balance. Okay, it's not obvious at all, but his idea is that it has to do with the microscopic reversibility of physical laws. So the kind of amount of, if you what's the physicist word for this? If you sort of cluster the physical states, that's not they talk about granules of it, then the kind of flow between region A to region B should be the same as from B to region A in steady state, just because the physical laws don't really care which way you're going. The process could run forward the same as it could run backwards. All right, so you have to read Onsager to see if you believe him making that argument, but that's the basis of his argument. So now I have to say, by far the bulk of research on Markov chains, and also, both not just in theory of algorithms and not just among probabilists, but also really in the mathematical physics literature, has been on reversible systems. Not all. In the last about 30 years and even more, there's definitely not, but the great bulk has been on this. So why? So in computer science, we have a really good reason, which is kind of the reason I already mentioned before, which is that this gives us kind of a magic formula for ensuring the steady state pi that we're looking for, right? So how do you actually guarantee that you're running a Markov chain on exponentially large space? That's always the interesting situation. It's an exponentially large space, all possible configurations of your system. So it's always exponential in how many bits you have to write down. How do you actually ensure that whatever it is you're converging toward is the state pi that you want to be in? Well, the fact that you can just subtract off the energies of two configurations and that tells you with what conditional probabilities to make the transfer, that's a very, very, very good reason. Otherwise, we have a hard time ensuring what steady state we're converging toward. Okay, even if we can show that we are converging. In physics, they have a different reason, somewhat related to what Onsager, Onsager sort of justified it, but in physics, the reason is because the basic thing, the kind of the first order thing that you're doing when you're studying, statistical physics, is you're studying systems that are at rest. Okay, just first to understand that. So there's water and there's ice and there's water vapor, and you want to understand those systems. You want to understand at what combinations of temperature and pressure you'll get one or the other, and you draw these kind of phase diagrams like I've brought you here on the lower right. So all of these systems are actually, by Onsager's argument, in steady state. So you don't really have any reason for departing from this until you look at much fancier things like fluctuations, the transition across equilibrium. But the fundamental theory is therefore about this. Now we come to the issue that really interests me, and of course Onsager didn't talk about, but people around the time of Boltzmann and did talk about, and they were worried about these kinds of questions. And this issue is this: something may be the steady state of a system, but if it takes more than the lifetime of the universe to converge to that, then it's not actually telling you anything about reality, right? So steady state is really only meaningful if your system converges quickly enough to get there, and so that you usually observe your system in that steady state. So what does characterize the convergence rate? So we have this large Markov chain. Let's suppose it's a continuous time evolution. So continuous time evolution of a Markov chain is given, and again, I hope you can see my mouse, by this exponential. You have the kernel, you exponentiate this kernel of the time evolution, and the kernel is the Laplacian. What's the Laplacian? It's P, the transition probability matrix, minus the identity. So this gives the continuous time Markov chain that for time evolution of your system. Also written, I'll use this delta throughout the talk to represent the Laplacian. And we say that the system converges if this continuous time Markov chain, if the actual e to the minus delta t converges to the outer product of the all ones vector that's telling you this is a row stochastic matrix with the pi, with the stationary state. Okay, so that's a way of, this basically says that from any starting state you are now close to pi. So the question is, what characterizes the mixing time? Well, if your matrix, if this Laplacian is symmetric, then your Laplacian has a real spectrum, and what really matters is the eigenvalue gap. Okay, you're going to have one trivial eigenvalue lambda 1 at 0. That corresponds to pi, the steady state. That's not going to budge. But what really matters is the gap to the next one. And so the convergence time is roughly 1 over this eigenvalue gap. Okay. Now, we often can't really analyze the spectrum. So in computer science, as you all know, we have these rich kind of techniques to get sort of combinatorial bounds that are roughly correspond to the same thing. And one of them is probably the most basic of those. There are little variants, but this is the basic thing, is what I'll call the edge expansion. It's sometimes called the conductance, but that term is kind of confusing. So I like to stick with edge expansion. And that roughly says this: you take the least bottleneck of the system. So you take your system. Here I've drawn a Markov chain on just 3 states, and I've said, I have a state one. I partition my states into 2 subsets: the vertex 1 and versus the vertices 2 and 3, and I look at how much conditional probability mass sits like in the upper right hand corner of this block decomposition. Okay. And if for every such partition, there's a lot of mass in the upper right block, that means that it's easy to escape every state, every set S of states, I should say. And so you look at the min of all overall sets, and you basically look for the worst. It's kind of like saying that there's an obstruction for mixing, and that obstruction is just, the single set S that's hardest to escape from. Okay. So the fact that this quantity phi, and we have techniques which I won't talk about at all right now for how to bound phi in all kinds of algorithmic cases that we care about. Now, phi is a substitute for lambda 2 due to the Cheeger inequalities for graphs. So lambda 2 is sandwiched between, and now we're going to get to something I want to focus on a little bit today. Lambda is the eigenvalue gap here is sandwiched between by what's called the easy Cheeger and hard Cheeger, that's kind of informal way of describing these things, by these hard and easy Cheeger inequalities sandwiched between 2 phi and phi squared over 2. So this is pretty much, in a nutshell, what we do with reversible systems. We bound phi, or we bound lambda, or we bound lambda by bounding phi, and then we teach whole courses about how to get a handle on phi.
Leonard, I had a quick question.
Yes, please.
So suppose we have an irreversible system. Is there a study or some kind of decomposition into a reversible system and something nice? Has that been looked upon at all? Does it make sense?
I don't think there is, unless you can be more specific about what you would
Yeah, I cannot.
What you would suggest as such a decomposition. I don't know of a way of.
In some context, people do think so, right? So, for example, this Brownian motion with drift is something like that.
Oh yeah. Okay. Brownian motion with drift is a little bit different. So there you have a superposition. There's something drifting, and then on top of that, yeah. The problem with that's absolutely. And sometimes, okay. The problem is that it's a little bit hard to not see that as rather special to a situation where you're in a, you're in a group, you're doing random walk in a group there, in a Abelian group even. There's a direction, and you can kind of superimpose, in a general graph, you're cycling around all kinds of cycles, and it's very hard to know what that would be. Yeah, I think it's
bolted on from top in some sense.
I'm sorry.
So in the Brownian motion of drift, this decomposition is sort of bolted on from top. So it's not like you come to it after.
Yeah, I believe it's special to examples like that. At least I personally wouldn't know how to define it for a general graph. I mean, it is a good it's definitely a good question. If physicists write, there are physicists that write papers about that. We'll talk about the symmetric exchange process later. I hope I get to it. And there are asymmetric exchange processes where there's a drift term, and they exactly analyze those by decoupling kind of a drift-free piece and a drift piece. So, yeah. But I do think that those are special. All right. So anything else? Break in. I'm rushing, but interrupt me. Okay, so I've talked a lot about passive stabilization. I want to now give you some examples of situations that are not covered by that, because it looks like such a great theory. Well, I'll give you some really, really, really obvious examples, and you'll see that actually most anything you want to talk about doesn't fall into these categories. So the terminology, though, is that now that we're doing some other thing, that some other Markov chain that has a steady state and it converges to it, it's ergodic, but it's not reversible. We're going to call it a non-equilibrium steady state. That's what physicists like to call it. So here's a picture of something that's designed to do that for its entire life cycle of existence, which is an insulator. What's the job of an insulator? Well, there's a hot water pipe running through the center there, and there's sort of cold air around the outside, and the entire job, the entire reason we manufacture these sleeves in the first place is so that from now and for 30 years to come, that bit of insulator sits in a temperature gradient. What's a temperature gradient? Temperature gradient is something that doesn't exist in thermal equilibrium. Well, it's not in thermal equilibrium. It is keeping something hot away from something cold and slowing down that transfer. So it's the job of an insulator in general is to be in a non-equilibrium steady state. That's its job. Okay. All right, that's a simple example. We can use this active stabilization in much, much more interesting ways than just being insulators. So I'm going to have to rush through this slide, but it is something that one should think about. So what are we? We're sitting here bathed in photons from the sun at about 5,800 Kelvin, and then the Earth re-emits these photons at about 290 Kelvin, more or less. Okay. This is more or less the heat equation of the heat system that's going on with the Earth. It's not the whole system because there's also radioactivity internal to the Earth. I'm ignoring that term. And so there's power coming in at about 200 watts per meter squared. Okay, that's about the power intake of the Earth from the sun. And then there's some other amount of power that's re-radiated. We'll call that P sub E. So there's power from the sun, P sub S. There's power re-radiated. It's called P sub E. This whole process is what's called a Carnot heat engine. You have hot sun. You have cool re-radiation to outer space. And the whole system as a total conserves entropy in total, not locally. And then so it's operating essentially as a Carnot heat engine. And you ask yourself, okay, what's the energy balance that's happening here? Well, there's a simple equation that says that when you have entropy conservation, that the power divided by temperature is the same for both of these heat baths. The hot heat bath and the cold heat bath, power over temperature or work over temperature is the same. So if you take the power being absorbed from the sun minus the power re-radiated to outer space, you factor it out as 1 minus the ratio of the temperatures times the power. And what you're left with is about 190 watts per meter squared. Okay, and that if you look at that white arrow down at the bottom of my kind of true to life picture that I've drawn there, that's the work, that's the power that's left over to run all kinds of interesting processes on planet Earth. So, for example, solar heating, separating fresh water from salt. Okay, that's a very important process for us. The sun does it from us. That's like this. And actually, everything in life is driven by such things. And you can actually, what happens is cycles upon cycles of cycles. We take this work and then we run Carnot cycles in the opposite direction. Everything is run by this kind of process, which is highly irreversible. I think for okay, I'll just say very briefly about this slide because I know I'm very short on time here. So one thing you should ask yourself is when we're designing Markov chains, for Monte Carlo purposes, for algorithmic purposes, would we actually benefit by using non-symmetric chains, irreversible chains, I should say? And this is not really well understood. There are certainly some interesting chains that people know that are not reversible, various kinds of card shuffling, but all the major algorithmic chains are reversible. So I'll just want to mention that there's a not very hard comparison lemma that I proved with my student. I'm not even sure it's new, but as far as we know, it's new. That says if I take any doubly stochastic P, so not generally symmetric, and I look at what's called its additive reversibilization or additive symmetrization. P plus P star. P star is the time reversal chain. Every Markov chain has a time reversal. If it's doubly stochastic, then it's kind of simple. You just transpose it. In general, you have to take into account Bayes' law. So the mixing is always faster for the asymmetric chain you started with than for the additive reversibilization. So up to some, you could lose a factor log n, but basically it could only help you to have been symmetric. We don't actually know, as I say, really powerful examples, really strongly motivating examples where you'd want to do this, but maybe some of you know of such examples. I don't know. Okay, there are artificial examples known where P mix is much faster than P plus P star. And a very simple example is if I have two rows or two cycles, a top cycle and a bottom cycle, and then each one of them you tend to do directed, you have a directed drift. So if on the top row here, you're drifting to the right at rate sort of 1 minus 1 over n and, cycling around. And the bottom row, you tend to go to the left, and you have a slow leakage between the top and the bottom. This system converges in linear time, whereas once you symmetrize it, you just get random walk on the cycle, and that takes quadratic time. Okay, so we can build examples where there's a big gap, but they're just not that interesting. All right, there's a slightly more interesting comparison lemma where, and I'm not even going to define this right now, where you can show that the effective resistance of P is less than or equal to the effective resistance between any pair of vertices in P plus P star over 2. And this is great because it tells you about commute times. But so it tells you commute times are faster, and this is not something obvious, that the commute time, in other words, if I have two pair of vertices U and V, the time to go from U to V and then back to U is less for the asymmetric chain than for the symmetrized chain. And I can't argue to you intuitively why that should be true, but it is true. All right. There's somewhat more related things that people have looked at. Probabilists have been looking at what's called non-backtracking random walk. Okay. And there are some results, but they're very, very precise. They're less interesting from the computer science point of view because they're gains of factors of 2 or something like that. They're very, very wonderful but precise results, but they're I'm not going to dwell on them because they don't have the kind of algorithmic implications that I'm interested in here. My next example of active stabilization is a very, very compelling one. This one's compelling enough that Yuval Rabbani and I wrote a paper about it recently. So let me tell you about economic markets. So what happens in a free market? You people come to market, they own something or they manufacture something and they offer it for sale, and everybody comes to the market and they trade freely and prices get established. And basically there's kind of a counter circulation. Goods, if I'm giving you goods, you're giving me money, and this kind of counter circulation. I'll talk about this in a little bit more detail later, so I'm not going to say anything more about it. I'll come back to it. Another really, really, really important case of active stabilization that is definitely not reversible is everything that we do for fault-tolerant computing. So on this left-hand panel, I want you to imagine you have a system. You're trying to store bits, but they're subject to noise. So on the upper left-hand side, you have this noisy code word, and it's getting corrupted. The kind of a thermal noise is kind of corrupting the bits in your storage. It may be a classical, it may be a quantum system. And you come along with cold bits, which we in quantum like to call ancillas, and in classical we just say known bits. That they're zeros, and then we do a reversible computation that's the actual error correction. And what happens is that you clear out this syndrome, which you can think of as hot bits. These are the leftover data that records where the error had been. And there's no way not to do that. Quantumly, you really have to do it explicitly. Even classically, it's actually happening, even if you claim that your code doesn't do it, but somewhere the memory of your computer gets erased, and that's where that happens. And you wind up with this corrected code word. This process, this fault-tolerant computing, is absolutely essential, certainly to getting quantum computers off the ground. And it is definitely not in the regime of reversible stabilization of systems. But we're trying to stabilize the code word at or very close to a code word, and we run these general algorithms. Another example, which I'll only illustrate, is control theory. Okay, so if you want to ride your bike, you're constantly applying some algorithm to kind of stabilize yourself and not fall over. That's a good friend of ours, I think, at the Athenaeum, Caltech. And definitely doing active stabilization. I don't know. I didn't see the frame after this, so maybe not, but I presume he did. Okay, so mathematical tools. Oh, we have precious little time. I'm going to rush through it. So what do we know about analyzing irreversible Markov chains? All that spectral stuff that I mentioned before, that for many of you was very tired stuff, that goes out the window. We don't have that necessarily. What do we have? We have, and I'm just going to talk about doubly stochastic matrices from now on, okay? It's sufficiently general. What we have left is essentially Perron-Frobenius. Perron-Frobenius tells you if I have a doubly stochastic matrix, the spectrum of its Laplacian lies in the unit disk centered at the point 1. If the chain is there's a root at 0. You can see that red dot over there. I hope here it is. There's a red dot. That root, again, if this is an irreducible, if it's an ergodic system, that root is simple, and the corresponding eigenvector is the stationary distribution. Okay, so hopefully this is very familiar to you. And irreducibility is sufficient to apply convergence in the limit. That is, that ultimately, when you apply and you look at this kernel e to the minus delta t, you converge to J, the all ones matrix divided by n. Okay, so here's the obvious question. Does the gap between 0 and the next eigenvalue actually determine the convergence rate, which is what it does for reversible chains, I'll remind you. Okay, there was just that gap that controlled everything pretty much, and except for very fine order. And what happens to this? So I'll return to that question shortly. So the Perron-Frobenius is one thing we know. And apart from Perron-Frobenius, there's kind of only one other thing that we know. And this is a theorem of Milena Mihail from 1989, and in which she shows that the edge expansion bounds still tell you convergence time of the Markov chain. Okay. Beforehand, I'll remind you, in the Cheeger, we said that lambda 2 was sandwiched between like phi and phi squared, which meant that the convergence time was sandwiched between 1 over phi and 1 over phi squared. And Mihail's theorem proves the same thing for systems, but not in terms of just directly for the mixing time, not through eigenvalues. Okay, so if we want to know whether the eigenvalue gap actually does predict convergence time, we have to ask ourselves, is there something like the Cheeger inequalities still for irreversible systems? So the question, answering this question starts off easy. It turns out that so-called hard Cheeger survives, and I'm going to skip through. It's due to a simple theorem of Fiedler that shows eigenvalue domination by the Laplacian of where the eigenvalue of the symmetrized chain is dominated by the eigenvalue of the unsymmetrized chain. So you have this comparison. So actually, the hard Cheeger side, the side that takes a little bit of work to prove, goes through fine. Hard Cheeger is what we should call an eigenvalue instability bound. It says, if I took a reducible chain really is a Markov chain that really broke into two completely separate pieces. Okay, when you have that, you have two eigenvalues at the origin for the Laplacian. Okay, and you can think of what this hard Cheeger is saying is that, look, as soon as you connect the system, the eigenvalue has to move away from the origin. The double eigenvalue at 0 has to move away from the origin. So it's an eigenvalue instability bound. It says lambda 2 gets repelled away from the origin as soon as we make the chain irreducible, as soon as we connect up the whole graph. So eigenvalue instability works great. Okay, and it's even easy to show. How about easy Cheeger? Easy Cheeger is an eigenvalue stability bound. It says if I'm pretty close to being a reducible chain, a chain that breaks into two pieces, then my second eigenvalue is pretty close to 0. That's what easy Cheeger shows. Easy Cheeger is really due in the non-graphical situation to Buser. So is this still true for irreversible chains? And not even is it true with a linear factor, which is this 2 phi, which is what we had, but is there any function of phi for which this is true? And the answer is no. Actually, I spent some time thinking about this problem, and I was very frustrated by it, and I kept not understanding why I couldn't prove it. And usually that's just because you're not smart enough, but occasionally it's because you're trying to prove something false, which is what turned out to be this time. Maybe there were some examples. There were some counterexamples, no, but they were tiny counterexamples. So not small chains, but the effect was very small. So there's the most beautiful example is this chain due to De Broglie, where the states of your system are bit strings of length k, and what you do in every step is you drop one bit off the end of your chain and then put a random bit at the beginning of the chain. Or I think I did it the other way around in the slide. Okay, so that's a very simple chain to describe. It's a very beautiful chain, has a lot of wonderful properties. So if, for example, down in the lower left of this picture of this slide, you can see what the spectrum of this chain looks like. It's got one eigenvalue. This is Laplacian, mind you. It got one eigenvalue at 0, and then all of the other n-1 eigenvalues are all at 1. That's not because it diagonalizes nicely like that. It's got just this horrible, well, that's not horrible actually. It's got a it's got a real Jordan form, lots of interesting Jordan blocks to understand. Okay, so it's a wonderful example to understand. If you're teaching a course about, Markov chains, this would be a fun one to give people to work on. So this is also, by the way, another example where symmetrizing the chain causes a quadratic slowdown, just like the 2 cycles example I gave you before. Okay, but this is just a factor of log n. If you're a computer scientist and you care about algorithms and something is slowing you down by a factor of log n is actually the complexity parameter, so it's a factor of n. It's not a huge deal. If you're worried about whether you can get a polynomial time algorithm for some problem or something, this is not a huge deal. Losing a factor of log n is interesting, but it doesn't change the fundamental kind of complexity theoretic or algorithmic point of view on this question. And so I spent a lot of time thinking, all right, now I know what the right thing to prove is. Now I know what I have to prove. I have to prove that it's Cheeger up to factor of log n. It's going to be phi times log n. So no. So it turns out that there's a violation by a factor of square root of n, we know. It's a huge surprise. And so basically eigenvalues just gaps just completely break down as predictive in the irreversible case. For lack of time, I am not going to even give you the cartoon version of what this Markov chain looks like. The paper was out in Soda last year. You can look back. I just do want to mention there is kind of a matching side. There is a stability bound of some kind. Okay, it's much weaker. It's bounded by a factor of n. There is something actually nice about it. So for those of you who know a little bit of numerical linear algebra will know that if you want to prove eigenvalue stability for non-normal operators, the tool that you use is something called Bauer-Feiche. Bauer-Feiche suffers an enormous cost in the due to the condition number of the matrices you use to diagonalize the matrix. Okay, that term, that cost does not actually appear here. You have to pay a factor of n, but you don't have to pay this other kind of factor. So those of you, I don't know, store it away. This might be actually something useful for you. The factor of n looks very large when you're dealing with algorithms, but in some other situation, it might be better than that condition number. We actually think that the correct factor is not square root of n. We think there should be an even worse example with a factor of n, but that's for the future. Both of these theorems I just told you about extend not just to doubly stochastic matrices, but actually to arbitrary matrices with non-negative entries. So this is kind of in the world of positive operators, but everything's finite. We're not doing anything, no operator algebras here. So I'll skip over this because I do want to get to talking about a little bit more. So 2 case studies. So I promised you before. So there are these 2 case studies. One is going to be about economic markets, and one about driven diffusive systems. And I'm going to drive myself through these 2 examples at top speed, unless interrupted, which you should still interrupt me. Case study 1. This is work with Yuval Rabbani. We wanted to understand Arrow-Debreu economies. So this was one of the things that motivated my interest in these irreversible systems, because. So you write down an Arrow-Debreu economy. For lack of time, it's all on the slides here. A brief version of it's on the slides here. An Arrow-Debreu economy has, as I said, a bunch of agents. They come to the market. They want to buy and sell. There is this wonderful theorem from the 1950s that says that in such a market, under some assumptions, what's called weak growth substitutes, there will be a Walrus point, which is a list of prices, so that so that all the goods clear, so everything gets bought by somebody exactly, and all of the agents are taking whatever money they earn from those sales and buying with them at those prices their favorite basket of goods. Okay, so the fact that these 2 conditions, 1 and 2, can coexist is a wonderful fact. And I put in this picture here of world trade flows just to emphasize how non-symmetric the process is. Okay, Australia sells grain to Japan and not vice versa. All right, it's just, Brazil sells soy to the Middle East and not vice versa. These things are extremely asymmetric. Okay, now in general equilibrium theory, this is a key theorem, is that there's a Walrus point. And it exists subject to a few conditions that I've written here. But the whole general equilibrium theory is only really about statics. Okay, it's about these equilibrium points. And some of the most famous economists in the world have actually kind of been bothered by this. So there's a great quote from Friedrich Hayek, where he says the starting point of the theory of competitive equilibrium, that means this kind of theorem like I quoted above, assumes away the main task, which only the processes of competition can solve, namely, how do we get ourselves to this market equilibrium? Why are we there in the first place? And again, this brings me back to the point I started this lecture from, which is we really care about, steady states are only important if the system can get there. And then Franklin Fisher writes, whether or not the actual economy is stable, we lack, a convincing theory of why that should be so. What gets us there? Okay. So, now, there is a good dynamic mechanism that could get you there, and it's actually the same dynamic mechanism that was used to prove these theorems, essentially, which is something called, and forgive my bad French, tâtonnement, which is where you slightly adjust your price when you're selling things. If you have excess demand, you raise your price. You have excess, you have less demand, you lower your price. Simple mechanism. You can write this down as differential equation. That's what I've done toward the bottom of the slide here. It's a perfectly rational thing for people to do, even though it doesn't fall into the what's called rational in game theory. And if you write down that kind of system of differential equations, you get something that really, really resembles the Ornstein-Uhlenbeck equation that I wrote for you beforehand. Okay, so let me move along here. I'm going to skip for, I'm absolutely going to skip these things here. So look at the equation in the middle of the slide. The alphas are like the logarithms of the prices. The time evolution, if you just look at the first term, there's a gradient term that's driving you there to what looks like a gradient term that's driving you toward the steady state, except it's not a gradient term. That is the non-symmetric Laplacian of this market. It's actually a quadratic polynomial but forgive me. Okay, so there's something that's driving you, that's contracting you toward the steady state. Okay, I really want you to think of this, that the market dynamics naturally contract you toward that steady state. That's essentially the context of how Arrow and DeBrew and Hurwitz and these people proved these theorems. But that process is not a symmetric matrix. And so we can't understand its rate of convergence using the spectral tools that we'd expect to use. And in fact, we don't know its rate of convergence, except that's what our paper is about, which I'm just going to mention, which is understanding these things, therefore, in terms of the edge expansion of the economic market. So it gives us a reason to take our concepts from computer science and combinatorics of edge expansion and actually carry them over to economic markets, and that helps us understand how quickly those markets converge. One more point I want to make about this equation in the middle of this slide is what happens if you also put a Brownian motion term. Okay, that's the second term there, t times a Wiener process. What happens to those? So now, of course, you're not going to converge to the equilibrium point. You're going to converge to a distribution over points. It is still true that the steady state of the price distribution is Gaussian. Okay, that doesn't care about the fact that the Laplacian is non-symmetric, but we really do not understand sort of, how quickly the system is going to converge to this system. So what I mentioned, this theory, I quoted Markovich and Villani, there's this whole theory with Lagutsobo inequalities, understanding how correctly that rate of convergence is for Ornstein-Uhlenbeck or Fokker-Planck. We don't have those tools. We don't have an equivalent theory of Fokker-Planck for these non-symmetric processes. Okay, so for those of you who know what those things mean, are interested in this, I think it's a lovely, lovely thing to start looking at. So, okay, and I am, okay, by my clock, I'm 2 minutes over, which is not good. And I have a few more slides. So
we can go a few minutes more.
Okay, I will try to. Let me just make one rhetorical point here, and then I'll quickly mention the work with Alistair Sinclair, and then I'll just go to the summary slide. I showed you that picture of global trade, and I'm sure you were absolutely transfixed by the movements of soy across the oceans. I want to bring that point a little bit home. Why you should care about markets with non-symmetric Laplacians. So a market with a symmetric Laplacian, or in other words, a market in detailed balance, is a market which at equilibrium is a barter economy. You come to the village square and you just made a really nice pair of sandals yesterday and you trade it for someone's, goat. And I'm sorry to put it in these village terms, but because it sounds very not nice actually, but the point is you cannot actually scale a large society in that way. And we know, in fact, that people used coins thousands of years ago, and this is why coins were developed way before a lot of other technologies. It's a really critical technology, money, and that's because, and here I've made my point, I hope, that people like you who are listening to this lecture if it weren't for money, if it weren't for the possibility of counter-circulating goods and money, you can only buy a car from someone who wanted really a lot of math tutoring, a lot. Okay, and that person, I mean, you could never be a car dealer in a university town, because how much math tutoring can you take? You can't build an economy this way. All right. So in any interesting economy, the steady state price vector is definitely not in equilibrium. It's what a physicist would call a non-equilibrium steady state. Okay. So let me move on and talk about driven diffusive systems. This is another very important class of systems where we are in steady state but out of equilibrium, and this is due to boundary conditions. Here you have a picture. There's the sea. Salt water kind of seeps its way through soil and into the fresh water. We have what they call a zone of dispersion. So you have gradients, either chemical gradients in this case, or it could be temperature gradients. And there's a nice mathematical model for this, which physicists have been studying for a few decades, called the symmetric exchange process, or the simple symmetric exchange process. You have this undirected graph, and in every turn you randomly pick an edge, and then you exchange, and every vertex, I should say, is either occupied or not occupied. It's 0 or 1. Okay. And in every round you pick an edge and you exchange what's the contents of the two vertices. Except the process becomes more interesting when there's boundary conditions. So in this picture, I have some graph, but on the left-hand side, I have a special vertex that's always occupied. If you empty it, it gets immediately refilled. And on the right-hand side, it's the opposite, the site that's never occupied. If you exchange with it, and that yellow vertex there, so here's the process. And if you see here, if this process happens, the yellow flees, but he's not there. He immediately flees from there. Okay, so this is a very important process study, system studied in mathematical physics. Very little is actually known about it outside of the one-dimensional, just the line. There's a wonderful paper of Schulman from 1983 that says something about very special systems in a higher dimension, but just slab boundary conditions. One nice thing, if you're a probabilist or you've been following in the last decade or so, people really worrying about negative association, is that this is the kind of the classic example of a system that maintains what's called negative association. So in fact, between any 2 points in this diagram, the probability that there's a negative correlation always, negative covariance of these two sites being occupied. So the system remains in non-equilibrium steady state. It's not reversible. It's of course carrying flow through it. If you filmed this process, you would see particles moving from left to right. That means it's not reversible. If I can show you a movie and if I filmed it in forward time or backward time, that means that the system is not reversible. So these systems with drift are certainly not reversible. But this kind of system, the only reason it's irreversible is because of boundary conditions. If you set the boundary conditions to, you took them away, let the system evolve without them, or if you put them both to be at the same temperature, it would be reversible. These systems are special. So that's my intermediate classification. I think it's a very interesting class of systems to study, is this kind of intermediate meso sort of reversible systems. The symmetric the dynamics themselves are symmetric, but there's a boundary-driven irreversibility. And we have some evidence that these are really special. So one bizarre thing that happens with these systems is that the symmetric exchange process on any graph with any boundary conditions has real spectrum. If you write down that Markov chain, you write down that matrix, we can show it that the eigenvalues of that system are always real. It's an incredibly strange result, because where do you usually get real spectrum? Usually from symmetric matrices. Okay, these matrices are not symmetric. Not only are they not symmetric, they're not normal. Not only are they not normal, they're not diagonalizable. Not only that, but I can show you that one of these situations is not diagonalizable on a graph with just 3 vertices. Okay, so the reason for real spectrum is quite strange, and maybe I'll just leave it with that tantalizing kind of result. I'll skip the rest. I'll just mention some questions. I hope I've given you many other questions to think about. I didn't really talk much about the fault tolerance example, but it's a really important question. If you have a cellular automaton, and you should be motivated mostly by the quantum example as you think about these, maybe. how much noise can such a system withstand and still compute? So fault tolerance, as I mentioned, is implemented by algorithms. It's not reversible. We don't know how to analyze. We don't have a theory for, we have ad hoc results, actually great ad hoc results. We don't have a theory for where the phase transition on too much noise occurs. In the reversible case, we do. In here, we don't have any kind of theory. We just have ad hoc results for a particular kind of algorithms. So how to characterize that? It's a big question. It's very interesting to study not just the symmetric exchange process. There are other interacting particle models that are even more interesting. One that I'm partial to these days is what's called the KMP process. I won't mention right now what it is. And then finally, for those of you who've been following this literature, a more technical kind of question, but a fascinating one, is there's a new definition of something. It's not quite edge expansion phi, something they like to call rho, a paper by Aaron Schild and by Miller, Walkington, and Wang, just from 2 years ago. Very nice new results where there's not this phi to phi squared gap. There's a theta of phi bound on the eigenvalue. And there's some question of whether anything like that would hold for irreversible chains, but I'll leave that open, and I'll stop here.
So thanks, Leonard, for the very interesting talk. So are there any? Is there one quick question?
I can ask a question if nobody else has one.
Yeah, sure, yeah.
Hi, Sandeep.
Hi, Leonard. So suppose we have a Markov chain, which, because this reversibility is a pairwise relation, so all the local interactions have to satisfy this pairwise property. So if you just break that property at a small fraction of the Markov chain, does that still give you something close to reversibility? I mean, are there properties which are continuous between reversible and these kind of systems?
That's a really nice question. I don't know. I would think that yes, because there's a result that I mentioned. I just mentioned briefly, but where we can compare a chain to its reversibilization and really matter. You wind up looking, of course, at the matrix difference between them. And if that has small, operator norm, then one can probably say something, but I don't know what it would be. So I don't have a direct answer. Only it feels like one should be able with these kinds of tools to say something.
Okay,
it's a good, nice question, actually.
So one thing that can go wrong is, I think you can make the stationary distribution can be very different, because you can have an absorbing state versus not an absorbing state.
Mm-hmm.
No, but let's take Sandeep's question in like a doubly stochastic P. Take a doubly stochastic matrix, and then just say it's very slight, that P minus P star has a very small operator norm. Then what? Can you now? Are the eigenvalues more predictive now of convergence time? Are they still predictive of convergence time or something? That's how I'd interpret Sandeep's question, perhaps.
Okay, so yes, so let's thank Leonard again for the talk, so maybe let's have a 2-minute break before the next talk by Varun, and in a couple of minutes. So that's at 10:14.
Thanks for having me.